So as I said, all the numbers can be represented, should be represented, namely all the numbers, alphabets, and the characters, everything should be represented in the binary numbers, and they'll be coded in as a combination of zeros and ones. Hence, it is said to be binary codes. And we know that digital system can read only zeros and ones, but as a human being, we knows only decimal number, and we both the human being as well as the digital system should interpret with each other for understanding what the data that we are going to give to the binary system, and in what form it is going to be saved and processed. And later, if we need to retrieve it from the binary system, we should know what is the data that it is giving. For that, we should know about binary codes. So binary codes or zeros and ones can be understood by your system, namely your digital system, any sort of digital system. And binary codes is nothing but combination of these zeros and ones to represent your symbol, your character, or any numbers, etc. For that, the combinations of zeros and ones, it will be in the digital system, it will be stored in the way of zeros and ones. And but as to custom design or to fit the digital system, we need to understand these binary codes. So based on which there are so many classifications of binary codes. Number one is weighted codes. We know about weighted codes already, because decimal system is a weighted code, and octal system is a weighted code. Whatever number systems we have read till now is all weighted codes, because each bit position will be having a weight that is said to be assigned a weight. But here similarly in this codes also, each bit position will be given a weight, and what are all the different types of weighted codes, I'll discuss shortly. So number 2 is non-weighted codes. And number 3 is alphanumeric codes. Both the first and second classification, whichever that we have seen here till now, the meaning weighted codes and non-weighted codes are used for representing your numbers. Whereas your alphanumeric codes is used for representing all your alphabets, characters, as well as numbers. And coming to the first classification, namely your weighted codes. Weighted codes are classified into reflective codes and sequential codes. Weighted codes, you have reflective code generally, and sequential code. Number 2 is sequential code. We will see one by one what are all the codes that is being covered in reflective codes. I'll repeat. Weighted codes are classified into 2 types: reflective codes and sequential codes. Consider this decimal number starting from 0 to 9. If 0 is the complement of 9 and 1 is the complement of 8, similarly 2 is the complement of 7. Likewise, if the numbers are complement with respect to each other in a given code, and that is said to be reflective codes. I'll share one screen. Okay. So weighted codes, as I said, we have different types of weighted codes. Some of them are listed here. Some of them are listed in the table. Number one is 8421 code. This code you know already. It's a simple normal binary code. because how will we will be writing a whole number of binary. So 2 power 0, 2 power 1, 2 power 2, 2 power 3, like this only it will go on and on. If you write a whole number like 1 1 0 1 like that, if I write without any decimal, so this binary number you will be representing it as each bit position will be having a weight, namely 2 power 0, 2 power 1, 2 power 2 and 2 power 3. So 8421 is a normal code that we already know. The 8421 is a normal code that we already know. And one more code is 2421, 2421, and again this is also a weighted code. Each bit position is having this weight, namely 2 power 0, 2 power 1, 2 power 2, 2 power 2 and again 2 power 1. Okay, these two are said to be weighted codes. These two are said to be weighted codes. Again the third one we won't be having in the power of 2. We won't be having in the power of 2, but each bit position will be having a weight, namely this is 2 power 0, 2 power 0, but this can't be 2 power 0, this is 5. But each position is assigned a weight, namely the first position, the 0th position is 1, the first position is 1, the second position is having a weight of 2 and the fourth position is having a weight of 5. So let us see how we will be representing a number, decimal number in these categories. So as I said, the 8421 code is a normal binary code. So I will be representing here. So 000, 0101 and 2 is 010 and 3 is 0011 and 4 is 0100 and 5 is 0101, 6 is 0110, 7 0111 and 8 1 followed by 3 zeros and 9 1001. This you know how you will be doing it, a decimal number to binary conversion, normal binary conversion. And and if you look at it, the second code, if you look at the second code, this is a 2421 code. Okay, compare this one with the decimal number. Now decimal number is 0, so all the numbers should be 0. And the next one is 1. So let me start from the LSB, least significant bit. So if I make this bit position, the first 0th bit position is 1, so it is equivalent to 1. And next one is 2. So make this as 0. The second position is 2 here. So make that as 1. And number 3. So 3 is 2 plus 1, 3. So 2 plus 1, 3. Both the bits are equal to 1. And number 4. 4 we have 4 here. So make that bit position alone 1 here. And the rest are all 0. And 5. Let me start from the LSB again. So 1 over here, 3. And this is 1. You should always start from the least significant bit. You should not make other combinations such 4 plus 1. Okay, start from least significant bits and then go on. And coming to the 6th bit position, 1011. So make it as 1100 and similarly 1101, 1110 and 1 all ones. And when you take 2421 code, see, look at these two here, this one and this one. Okay, this is all 0, this is all 1. So 0 and 1 is complement with respect to each other. Similarly 2 and 8. Okay, 2 and 8 are complement with respect to each other. Hence this code, namely 2421 code, not 8421 code. 2421 code is a reflective code. Is an example for reflective code. And similarly, if you take this, I hope this one 5421 and is also a reflective code. 5211. 5211 is also a reflective code. Okay. Whereas coming to 8421 code, it is the second category. What is the second category we have read? We have weighted codes are classified into two types. One is sequential code and number 2 is reflective code. We have seen the examples of reflective code, whereas 8421 is a sequential code. Sequential code is nothing but what is that? Namely 1 is higher than the 0. The succeeding number will be higher than the preceding number. The succeeding number will be higher than the preceding number. So when you compare this, this is higher than this, whereas 1 is higher than the previous one, and similarly 2 is higher than 1 when you compare these two. So that is, if you add 1 to each other, if you add 1 with each other, you will be getting the sequential code. A sequential code, a code is said to be sequential when each succeeding code is one binary number greater than its preceding code. Okay, if you add 1 with respect in the preceding number, you will be getting the next number. You will be getting the next number. So 8421 code is said to be sequential code, one of the sequential code. And other than this, other than these two sequential code, 8421 code is 8421 is this is a sequential code, whereas 2421 and 5211 is said to be reflective code. One more reflective code we need to study, that is Xs3 code. Xs3 code. Okay. Xs3 don't come under weighted codes, it will come under non-weighted codes. We'll see non-weighted codes. Okay, what we have seen here as an example is, we have seen weighted code. Weighted codes, 3 weighted codes we have seen, 8421, 2421 and 5211, of which 2421 and 5211 are said to be reflective codes, whereas 8421 is said to be sequential code. And coming to the non-weighted codes, you have different types of non-weighted codes. One is Xs3 code, and number 2 is gray code. Number two is gray code. Xs3 code, it is nothing but 8421 code. We have already read this normal binary code. If you add plus 3, the decimal number 3 with it, you will be getting the Xs3 code. You are getting me? For example, 0, the first number in the normal 8421 code, the decimal number, and this is 8421 code, and 0 and 0 will be represented here. If you add 3, what is the binary equivalent of 3? It is 0011. If you add 0011 in the 8421, you will be getting the equivalent Xs3 code. So this will be 0011. Okay, this will be 0011. So similarly, all the codes, all the decimal numbers from 0 to 9, you can generate it in the table. You can generate this in the table. Next one, this is a non-weighted code, meaning each bit position doesn't have any weight. It's non-weighted code. You have 2 classifications of non-weighted code, namely 8421 and the gray code. So gray code, I'll just share one figure to you. Why we are and gray code, there will be only 1 bit change between the preceding and the succeeding number. Between the preceding and the succeeding number, there should be only 1 bit change. Okay. So for example, here, let me go ahead here and then go back to the diagram. So 0 will be represented in a normal 8421, it is 000, and 1 will be represented as 0001, whereas 2 will be represented as 0010. Okay, 0010. So if you see these two number, and you know already 8421 code is a sequential code. This is sequential code. What is sequential code? Sequential code is nothing but when the succeeding number is higher by 1 bit. It is higher by 1 bit than the preceding number. Such codes are said to be sequential codes. So now when you compare this 1 and 2 decimal in terms of 8421, see here 1 is changed to 0 and 0 is changed to 1. Consecutively 2 bits are changing here. Such a bit change is not allowed in gray code. Only 1 bit change is allowed. So what they will do here is, see, they will retain this bit as such, okay, and they are going to change the next higher bit from 0 to 1. So 0 to 1, 0 0 1 1 0 0 1 1, because in gray code only one bit change is allowed. Only one bit change is allowed. I'll share on screen. So consider this binary code. Binary code, we know generally how will be the transition of bits from 0 to 7, namely 001, 002. Consider this as a disk recorder. Consider this as a rotating disk that must give a output of the position in the 3-bit binary. Okay, so we have 3 brushes in each sector, namely zone 1, assume this as zone 2, zone 3. For the 3 bits, you have 3-bit variations, 2 power 3, it is 8 combinations from 0 to 7. So from 0 0, all 0 to all 1, you will be having 8 combinations. So what we need to do is, this rotating disk, we need to when this disk is rotating, when this disk is represented by a line, and in the disk we have 3 brushes, brush 1, brush 2, brush 3, to read the data from each zone, If the brush is on the black or the shaded portion, the brush will read that portion to be 1. If this is in the white portion, if the brush is in the white portion, then that data will be read as 0. And keep in mind, all the 3 brushes has to be moved synchronously with respect to each other, but that can't be possible if slightly if one brush head is moving ahead slightly. For example, see, consider this triple one, all the brush in this zone has to read 1 1 1. All the brush has to read 1 1 1. If assume that if brush 3 is slightly ahead with respect to other 2 brushes when it is coming to this edge of this zone, so what this will be read as? This will be read as 0 1 and 1. This will be read as 0 1 and 1. Similarly, in the case of 0 0 0, when the brush is moving, all the 3 brushes is assumed to move in this zone. When one brush is slightly again assume that one brush is slightly ahead, brush 3 is slightly ahead with brush 2 and brush 1. When this is read, so it will be read as 1 0 0, which is an incorrect data. That is, the rotating disk is reading an incorrect data. To avoid that, or to minimize the error that the brush is reading in a case of rotating disk position, rotating error position, what they have developed is a gray code. So in the gray code, only 1 bit change is allowed. So they thought that they can minimize, they cannot nullify the error, but they can minimize the error that is occurring when we are reading it from a rotating, when we are reading the data from the rotating disk. So here that is how your gray code was developed. And in gray code, as I said earlier, only 1 bit position is allowed. So from 0 0 0, from 0 0 0 to 0 0 1 and 0 1 1, again only 1 bit change is allowed. So retain this as such, 0 1 0 1 1 0, like that it will go on and on. So this is regarding your gray code. Or as I already said, Xs3 is nothing but 8421 code, normal binary code plus 3. If you add, you will be getting the Xs3 code. We will solve one example of converting a binary number to the gray code and gray code to binary code, vice versa. So the first problem, so convert the binary number 1001, okay, 1001 011. This is a binary number. Convert this to a gray code. Okay, convert this to a gray code. How? So this is 1 0 0 1 0 1 1. So how to convert this as gray coders? Retain the MSB as such. Okay, retain the MSB as such. Then, okay, later you add these two number. Okay, 1 plus 0. 1 plus 0, we know that it is 1. Am I right? Huh? So, 0 plus 0 is 0. 0 plus binary 1, it is 1. Sum is 0. Okay. So, similarly, 0 plus 1, sum is 1. 1 plus 0, sum is 1. 1 plus 1, if you see 1 plus 1, if you add decimal is 2, as I said already. 2 when I divided, 1 0. So, I will be writing in this way. Okay. Sum, this is your sum, this is your carry. Sum is 0, carry is 1. Okay. So, now add successively each bit position and retain here. So, 1 plus 0, it is 1. Again, 0 plus 0, it is 0 here. And then 0 plus 1, so it should be 1 here. 1 plus 0, it should be 1 here. 0 plus 1, it should be 1 here. 1 plus 1, sum is 0. So, sum is 0. There is a carry. Ignore your carry. Okay. Ignore your carry. Shall I give one more example to solve for you? Take this and convert it. Take a simple number. 1011 binary. Convert this into gray code. 1110. Yeah. This is the right answer. Right. So let me go ahead with vice versa combination, namely, from gray code to binary. 1 0 1 and 1. Okay, 1 0 1 and 1. Here also retain your MSB as such. Retain your MSB as such. Now what we need to do is you need to add like this. This 1 plus 0, your resultant is 1, and this 1 plus 1. Okay, this 1 plus 1, what is 1 plus 1? Sum is 0. Ignore your carry, and then 0 plus 1, it is 1. See, this is 1 0 1 and 1. Retain your MSB as such. Okay, retain as your MSB as such. Now add this MSB with the next succeeding number. Okay, this add this one. 1 plus 0, it is 1. Okay, now I am having the second digit. Now add the second digit with the next succeeding number. Add this one. 1 plus 1, you will know 1 plus 1 is 2. So I said already 1 plus 1 is binary 2. We have sum 0 and carry 1. Ignore the carry. We need to ignore the carry. The sum we need to retain. So 0. Okay. Ignore the carry. So next one, what is that? 0 plus 1, your resultant is 1. Okay. So 1011 can be written as 1101. Okay. So now just do this conversion. 1 0 0 1 0 1 1. Convert this gray code to binary. Convert this to binary. 111
00
10, right.
11.
Okay, this is how you will be converting the gray code to binary. Your gray code to binary. Then we will move on to the next bit. Next code. That is your error detecting codes. Error detecting codes. This will be when digital data has to be transmitted from one place to another, ensure that the data is transmitted. The data is transmitted correctly. That whatever I am receiving, the digital data I am receiving is the correct data. So for that, certain codes are developed. One among them is error detecting codes. So how they have detected the error? For example, they have simply used a bit called parity bit. Meaning you have two types of parity here. One is odd parity and another one is even parity. As I said earlier, data will be transmitted in terms of bytes. And it will be stored in terms of bytes. So parity bit, it is a single bit. So D0, D1, Okay, I need to transfer in terms of 8 bits. Keep in mind that D2, D3, D4, D5, D6, we have 7 bits here. These are said to be data bits, and along with the data bits I'll be adding the parity bit. Okay, this parity bit can have any combination, either 0 or 1. Okay, either 0 or 1. Keep in mind, if number of bits in including the data bits, if we have even number of ones, say for example, if I'm having let this be 1, okay, and 0 0 1 1 0 1 1 2 3 4 0. So here, including the parity bits, we have 8 bits of data. So including the parity bit, how many number of ones we are having here? 1 2 3 4. I'll be having 4, which is an even number. Okay, which is an even number. If I have even number of ones in the byte transmitted or received, such a parity is said to be even parity. In this case, we are having 1 2 3 number of ones, which is an odd number of ones in the data that is being transmitted or received. So this data is having an odd parity. Okay, that is the meaning. For example, we have a sending end, and we have a receiving end. Okay, receiving end. So if the data is transmitted, let me write it in decimal. What if we are transmitting 1001 1010 at this sending end, and in the receiving end, if I am receiving 1001, okay, 1011, okay, 1011. See, we know what we will send in the information. This here it's an odd parity, an even parity. But 1 2 3 here it is 5 number of ones. But whatever we are receiving here, it is an odd parity. Am I right? We can detect the error here. We can detect the error that we have received a wrong data. That we have received an wrong data. See, only one bit of error if it is occurring, we can detect here. For example, instead of 1001 1011, if I am receiving it as 1001 1111, okay, all are ones. If you check 1 2 3 4 5 and 6, here we have even number of ones. So what we will assume that we have received a correct data because it's an even parity, but it's not like that. Right, we have two errors in two data bits, So to overcome this, what they have done is, the next step what they have done is, they have used checksums. What is that checksum is? For example, if I am transferring the first byte, let me assume that I am transferring the first byte A as 10110111. Okay, then I am going to transfer the second byte. Okay, that is 00. Let me assume that 001 00010. Okay, if I am transferring 2 bytes one after the other, later what I will do is, I will add these two. In the sending end, what they will do is, they will add these two, they will sum these two. The sum number is 1101100001. Okay, this is the sum. Okay, in the sending end, they will be sending first, they will be sending A, second they will be sending B, third they will be sending the sum also. At the receiving end, they will receive all the three, and with respect to sum, they will check A and B whether they have received the correct data or not, whether they have regarding your checksums. Okay, the next one is parity data code. Okay, parity data codes. We have used parity bit in the only in the most significant bit, only in the MSB. Am I right? Only we have assigned the parity bit as the MSB bit, most significant bit. Instead, if we have parity bits within the byte of data, within a byte of data. It may be anywhere in the data. It may be anywhere between 0 to 7 in the data. If the parity can be contained within each character or within each byte, okay, within each byte, such a sort of codes are said to be parity data codes. Such a sort of codes are said to be parity data codes, and in each we are going to see two such codes, parity data codes. We have two types of parity data codes. One is 2 out of 5 code, okay. Number two is biquinary code. See here, 1 is represented by 2 out of 5 code. We have 5 digits of binary, 1 2 3 4 and 5, out of which when you consider each digit, you will be having only 2 ones. Keep in mind, biquinary, how to remember, this one is, you will be having 0 1, you have 6 7, 7. So out of which 0 1 means it will be 0. 0 1 in the biquinary, it will be 0. It will be 0. The first number, if you see, that is 0. Whereas this and all, the normal 1 0 0 1 is 0 0 1 0, again 1 2 3 4. This you have to retain as 1, and again 0 1 2 3 4. The same number will be repeated here in biquinary form. So only this 2 digits, namely 6 and the 7th bit is changing. The other bits are same, 0 0 0 1 0 0 0 1 0 0 1 0 0 0 1 0. Okay. Rest 2 out of 5. You need to remember somehow. There is no other go. So it is from 0 to 9. So it is 1 1. Only 2 ones you will be having in each digit. 2 ones you will be having in each digit. We have seen error detecting codes. We have seen parity, using parity bits. We have done error detecting codes, and we should know about error correcting codes also. Simply detect the error, it is of no use. We need to correct the error also in the data that is being transmitted. It will be helpful in telecommunications, and based on which a scientist called Hamming, okay, detecting code. It is otherwise said to be Hamming code also. This is otherwise called as Hamming code since it is developed by Hamming. So what he has done is, he again, as I said earlier, only a byte of bits will be transmitted to from the sending end to the receiving end. So we will be transferring 8 bits at a time. So here what Hamming used is, he have used 3 parity bits, okay, and he have used 3 parity bits, 4 data bits. He have developed a code with 7 bits, okay. He has developed a code with 7 bits. So his bit positions are parity bit P1, parity bit P2, data bit D3, parity bit P4, and data bits D5, D6 and D7. This is his code. Namely, this is how he structured his code. So now he has 3 parity bits, namely P1, P2 and P4. Okay, P1, P2 and P4. He has 3 parity bits, P1, P2 and P4. So what we have done is, when he uses P1, along with P1 he have used P1, D3, D5, D7, and when he uses P2 he have used P2, D3, D6, D7, and again when he used he have used P4, D5, D6, D7. This is how we have used, and he have developed only even parity. Okay, there is no odd parity in Hamming code. There is only even parity in Hamming codes.